let's continue working on factoring with factoring trinomials and the difference of squares pattern. So in these notes, we're going to look at factoring trinomials in the form ax squared plus bx plus c. So trinomials, meaning they have three terms. And we're also looking at factoring binomials in the form a squared minus b squared, which is a difference of squares. So first, just a reminder, when you multiply two binomials together using the distributive property, you usually get a trinomial at the end. So for example, if we multiply 2x plus 3 times x plus 5, using the distributive property, so 2x times x is 2x squared, 2x times 5 is 10x, 3 times x is 3x, and 3 times 5 is 15. After combining like terms, we get 2x squared plus 13x plus 15, which is a trinomial, three terms, in the form ax squared plus bx plus c. And so to factor this trinomial, we would want to work backwards through that distributive property to arrive back at this factored form. So the way we do that from the trinomial step is typically referred to as the AC method. Sometimes people might use a big X to organize their numbers. But basically you find two numbers that multiply to AC and add to B. We split the middle term using those two numbers and then factor by grouping, which we looked at in the 3.2 notes. So let's try this. So factor each trinomial and look for a GCF first. Always a good idea to look through for an overall GCF before we start. So for example, 1a, we do not have an overall GCF, and we're trying to find AC, two numbers that multiply to AC and add to B. Well, AC here, A is 1, AC is 20. So we want to find two numbers that multiply to 20 and add to 9. So got to think about that for a second. So it can be helpful to consider all the factors of 20. 20 can be multiplied 1 times 20, 2 times 10, 4 times 5. And 4 and 5 right here are the numbers we're looking for because they multiply to 20 and add to 9. So what we're going to do is split that middle term, that 9x, we're going to split that into 4x plus 5x. We still have the x squared, still have the 20. What this allows us to do now is use our grouping method because now we have four terms. So I can take out of the first two an x as the GCF, leaving x plus 4. And out of the second two, I can take out a 5, leaving x plus 4 as well. So my final factored form here is our binomial in parentheses, x plus 4, and the leftovers, x plus 5. Now I would like to note that these numbers here, x plus 4 and x plus 5, are the same numbers we found here, the two factors that multiply to 20 and add to 9. And this will always happen when you have a leading coefficient of 1. When 1 is your A value, the two numbers you find that multiply to AC and add to B will always be the numbers that show up in your factors at the end. So if you're confident about that and you trust that statement, you can go straight to the answer once you find those two numbers if your leading coefficient is 1. Now, for example, B, our leading coefficient, is not 1, so we can't use this trick. So we can do the math, though. AC here is 6. So we're trying to find two numbers that multiply to 6 and add to 5. Well, 6 doesn't have too many factors, so I believe we're looking for 2 and 3. 6 can be multiplied 1 times 6, 2 times 3, and 2 and 3 are the two numbers that multiply to 6 and add to 5. So we'll split that middle term again. We've got 3x squared plus 3x plus 2x plus 2. Now, it doesn't matter which order you write those numbers in, we will get the same answer at the end. Just to show that, maybe I'll go ahead and do it both ways. 3x squared plus 2x plus 3x plus 2. So we'll see we get the same two factors. So in the top row, my original polynomial that I wrote, I can take out a 3x from both of these, leaving x plus 1. And then I can take out a 2 from both of these, leaving x plus 1 as well. So my final factored form of this polynomial is x plus 1 and 3x plus 2. It also doesn't really matter which order you write this in. I could have written the 3x plus 2 first. Either way is fine. Now, just to show you that we'll get the same answer no matter which way we write those two middle terms, from the bottom polynomial here, I can just take out an x from this first set, which gives me the 3x plus 2. And I can take out a 1 from the second set, leaving 3x plus 2. And so all it changes is the order that my factors show up in. Here, the thing in common in the parentheses is 3x plus 2. The leftovers are my x plus 1, but it's the same two factors that I get here. Okay, so that's just to show that it doesn't matter what order you write those middle two terms in. Whether you want to organize them, here we have the 3x close to the 3x in the first one, or other way around, it doesn't matter. You get the same answer. From now on, we'll just do them one time. We won't do them both ways. But notice I did not have a leading coefficient of 1. I had a leading coefficient of 3. And so the numbers that we found here are factors a little more complicated than that. So whereas on example A, the two numbers we found were exactly the two numbers that were in the factors at the end, 4 and 5. Didn't work out the same way here because my leading coefficient was not 1. Okay, example C, something to watch out for here is we do have a GCF we can take out at the beginning. We can divide everything by 3, leaving 2r squared minus r minus 3. Now you don't have to do that. You can always take it out at the end, but it will make your work easier in the meantime. So now my AC numbers are 2 and negative 3, which gives me negative 6 for AC. I'm looking for two numbers that multiply to negative 6 and add to negative 1. Well, now negative 6, it depends on which number you put the negative on, right? So 6 is 1 and 6 and 2 and 3, like we just saw in the previous example. But I'm looking for a sum of negative 1. So that means my negative has to go on the bigger number. So my two numbers I want here are 2 and negative 3. So we're going to split that middle term. 2r squared plus 2r minus 3r minus 3. Now we can factor using grouping. I can take out a 2r from the first set, leaving r plus 1. I'll take out a negative 3 from the second set, again leaving r plus 1. So my final factored form here is r plus 1 times 2r minus 3. And don't forget the 3 we took out at the beginning. That is important as well. Okay, so that is a brief course on the AC method. And like I said, I know that some people may have learned to use a big X to organize their numbers, but essentially you have to do the same work anyway. Now let's talk about the difference of squares pattern. So this is where, if you have a binomial, which is a perfect square minus another perfect square, a squared minus b squared, the factored form is always going to be the square roots of those perfect squares, a plus b and a minus b. And this is because when you multiply this back through, we get a negative ab and a positive ab that cancel each other out for that middle term. So the difference of squares pattern becomes relatively easy. Basically, you have a b value of 0. So if I was going to do this the same way I would factor a trinomial, I could think of this as m squared plus 0m minus 64, and I would look for two numbers that multiply to negative 64 and add to 0, which would be negative 8 and positive 8. But they will always cancel out in the middle. And so to avoid having to do all that other work, we can just follow this pattern, and it's a plus b, a minus b. So for m squared minus 64, the square root of m squared is m. The square root of 64 is 8. So I have m plus 8 and m minus 8, and that is all I need to do. For example B, 16y squared and 81z squared, those are both perfect squares. So I can factor that out as 4y plus 9z times 4y minus 9z. Always a good idea to double check afterwards that you don't have another difference of squares in this subtraction one. This is not, because y and z aren't perfect squares, but 4 and 9 are, so it could have been. It's a good idea to check that. Also, it's important to first check for a GCF. So on example C here, we can take a 3b out before we start. And that will leave b squared minus 9. So it wasn't a difference of squares, but after we take out this GCF, it is a difference of squares now. So our final factored form would be 3b times, and the square root of b squared is b, the square root of 9 is 3, so b plus 3 and b minus 3. Example D, we have x to the 16th minus 81. Now you know an exponent is a perfect square if it's even. It basically can be divided by 2. So for a whole number, it has to have a number times itself to equal to it. But for an exponent, it just has to be even. So the square roots here are x to the 8th divided by 2 plus 9 and x to the 8th minus 9. And if we check that, these are also perfect squares. So our final answer, hopefully, is x to the 8th plus 9. That one didn't change. X to the 4th plus 3, and x to the 4th minus 3. And that is all there. Even though x to the 4th is a perfect square, 3 is not. So that is our final factored form there. Always a good idea to double check afterwards to make sure that you don't have another difference of squares that you can factor out. Example E here, we have m to the 4th minus 1. So again, this is even, 4 is even, and 1 is always a perfect square because 1 times 1 equals 1. So this is m squared plus 1 and m squared minus 1. And so again, we have another difference of squares right here. So our final answer, m squared plus 1, doesn't change. Then we get m plus 1 and m minus 1. One more thing to notice is how the degrees can help you predict how many factors you get. So here we have m squared, and I have 2 factors, m plus 8, m minus 8. Here we have squared, squared, just 2 factors. Here we had a cubed. So what that means is we're going to have 3 b to the firsts in there. B times b times b, b to the 3rd. It won't always work out perfectly. For example, on example D here, we had 16. So basically all of the numbers in our answer have to add up to 16, right? We have 8 and 4 and 4. And this 4 means we had 2 and 1 and 1. So that can help you kind of predict or anticipate that you may have more than 2 factors at the end. If you have a higher exponent than just 2, it can mean that you're going to have to look for more and more differences of squares afterwards, or a GCF like we saw in example C. So there's the difference of squares pattern. a squared minus b squared equals a plus b, a times b, or a plus b times a minus b. And then the AC trinomial method, split the middle term and factor by grouping.